Welcome! In this session, we will explore LeetCode problem number 532, titled K-diff pairs in an array. This problem challenges us to identify pairs of integers in an array that have a specific difference, offering a great opportunity to deepen our understanding of array manipulation and hash-based approaches. Let's dive into the problem and uncover the optimal solution. In this problem, you're given an integer array called nums and a non-negative integer k. The goal is to determine the number of unique K-diff pairs in the array. A K-diff pair is defined as a pair of numbers from the array, denoted as nums I, nums j, where the indices I and j satisfy two conditions: they must be different, and the absolute difference between the two numbers must equal k. It's important to note that the order of the pair doesn't matter, so nums I, nums j is considered the same as nums j, nums I. Additionally, the array may contain duplicate elements, but we only count unique pairs. The input includes the array nums, which can have up to 10,000 elements, and the integer k, which can be as large as 10 million. The output is a single integer representing the count of these unique K-diff pairs. Now, let's look at some examples to better understand the problem. In the first example, the input array is nums equals 3, 1, 4, 1, 5, and k equals 2. The output is 2, because there are two unique pairs that satisfy the condition where the difference between the numbers is exactly 2. These pairs are 3, 1, and 5, 3. For 3, 1, the calculation is 3 minus 1, which equals 2. Similarly, 4, 5, 3, the calculation is 5 minus 3, which also equals 2. These pairs are unique, so we count both. In the second example, the input is nums equals 1, 2, 3, 4, 5, and k equals 1. The output is 4, as there are 4 unique pairs where the difference between the numbers is exactly 1. These pairs are 2, 1, 3, 2, 4, 3, and 5, 4. For instance, in the pair 2, 1, the calculation is 2 minus 1, which equals 1. Similarly, this is true for the other pairs. The pairs are distinct, so all 4 are counted. In the third example, the input is nums equals 1, 3, 1, 5, 4, and k equals 0. The output is 1, because there is only one unique pair where the difference is 0. That pair is 1, 1. Since duplicates are allowed in the array, we can form this pair, but we count it only once. To clarify further, for the third example with k equals 0, the pair 1, 1 is valid because the condition nums I, nums j equals 0 is satisfied. However, even if there are multiple occurrences of the number 1 in the array, we count this pair only once because we are calculating unique pairs. Moving on to the constraints, the array can have between 1 and 10,000 elements, and each element can range from negative 10 million to positive 10 million. The value of k is constrained between 0 and 10 million. For edge cases, if k equals 0, only identical elements in the array can form valid pairs. If the array has no duplicates and k greater than 0, the count depends on whether the array contains elements differing by exactly k. If k exceeds 10 million, the result will always be 0 because the maximum possible difference between any two elements in the array is limited by their range. Lastly, if the array has fewer than 2 elements, no pairs can be formed, so the result is 0. To tackle the problem of finding K-diff pairs in an array, we explored several approaches. The first approach is the brute force method. Here, the intuition is straightforward: iterate through all possible pairs of numbers in the array and check if their difference equals the given value k. To do this, we use 2 nested loops to generate every pair, then verify if the pair satisfies the K-diff condition. To ensure we don't count duplicate pairs, we can use a set to store unique results. However, while this method is simple to implement, it comes with a major trade-off. Its time complexity is n squared, due to the nested loops, which makes it impractical for larger arrays. The space complexity is n, because of the set used to store results. Recognizing these inefficiencies, we turn to an optimized approach using a hash map. The intuition here is to leverage a hash map to store the frequency of each number in the array. This allows us to check the existence of required numbers that satisfy the K-diff condition in constant time. Building on the hash map approach, we start by counting the frequency of each number in the array and storing it in the hash map. Once we have this frequency map, we iterate through its keys. If k equals 0, we check if any number has a frequency greater than 1, indicating duplicates that form valid pairs. If k is greater than 0, we check if the value number plus k exists as a key in the hash map. For every valid case, we count the pair. This approach significantly improves efficiency, with a time complexity of O(n) for both building the hash map and iterating through it. Space complexity is also O(n), since we are storing the frequency of each number. While it avoids the quadratic time complexity of the brute force method, it does require additional space for the hash map. Another alternative is the two-pointer technique, which relies on sorting the array. Once the array is sorted, we use 2 pointers, left and right, to traverse it. When the difference between the values at these pointers equals k, we record the pair and move both pointers to avoid duplicates. If the difference is less than k, we increment the right pointer. If it's greater than k, we increment the left pointer. This ensures we efficiently find all valid pairs. The two-pointer approach comes with its own trade-offs. While it avoids the additional space required for a hash map, it requires sorting the array first, which takes O(n) log n time. This makes it less efficient than the hash map approach when working with unsorted data, especially for larger input sizes. After evaluating all 3 methods, we chose the optimized hash map approach as our preferred solution. This decision is based on its linear time complexity and ability to handle unsorted data efficiently. The key insight here is recognizing that the hash map enables direct existence checks for number plus k or handling duplicates when k equals 0. This eliminates the need for nested iterations, drastically reducing computational overhead compared to the brute force method. As for the two-pointer method, while it is space-efficient, the sorting step introduces additional overhead, making it less practical for this problem. In summary, the brute force approach is too slow to handle larger inputs, the two-pointer approach is less efficient for unsorted data, and the hash map approach strikes the right balance between speed and memory usage. For these reasons, the hash map approach is the most scalable and efficient solution for finding K-diff pairs in an array. In this problem, we are tasked with finding the number of unique pairs in an array where the absolute difference between the elements equals a given value, k. These pairs are referred to as K-diff pairs. To qualify as a valid pair, the 2 elements must be distinct, and the absolute difference between them must exactly match k. For example, if k is 2 and the array contains the numbers 1 and 3, the pair 1, 3 would be valid because the absolute difference is 2. To solve this efficiently, we will use an optimized approach that leverages hashing. This will allow us to reduce computational overhead compared to a brute force method while still ensuring correctness. First, we need to understand the inputs and outputs of the problem. The input consists of an integer array, nums, and an integer, k. The output is the number of unique K-diff pairs in the array. Importantly, we must ensure that each pair is counted only once, regardless of the order of the elements. Additionally, we need to handle edge cases. For instance, if k is negative, we can immediately return 0 because absolute differences are always non-negative. Similarly, if the array is empty or contains only one element, no pairs can be formed, and the result should also be 0. To begin solving the problem, we use a hash map to count the frequency of each unique number in the array. This frequency map allows us to efficiently check for the presence of specific values needed to form valid pairs. For example, if the array is 1, 2, 3, 4, 5, the frequency map would store 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, as each number appears exactly once. Once we have this map, we can iterate through its entries to identify valid pairs. We initialize a counter to keep track of the number of valid K-diff pairs. For each unique number in the map, we consider 2 cases. First, if k equals 0, the only way to form a valid pair is if the current number appears more than once in the array. For example, in the array 1, 1, 1, 2, with k equal to 0, the pair 1, 1 is valid because 1 appears multiple times. Second, if k is greater than 0, we check whether the number plus k exists in the frequency map. For instance, in the array 1, 2, 3, with k equal to 2, the pair 1, 3 is valid because 3 equals 1 plus 2. For each valid pair identified, we increment the counter, and after processing all numbers in the map, we return the counter as the result.
There are several key insights that make this algorithm both efficient and correct.
First, the use of a hash map ensures that we do not double count pairs. For instance, the pair 1, 3 is considered the same as 3, 1, and by iterating through unique values, we only count it once.
Second, handling the case where k equals 0 separately is crucial.
In this situation, we need to check for duplicates of the same number, as the valid pairs involve the same element repeated. Third, the efficiency of the hash map is a major advantage. Checking for the existence of a specific value, such as number plus k, can be done in constant time, which significantly reduces the overall computational complexity. Speaking of complexity, the time complexity of this algorithm is O(n), where n is the size of the array. This is because constructing the frequency map requires O(n) time, and iterating through the map also takes O(n). The space complexity is also O(n), as the hash map stores up to n unique elements. Together, these insights and efficiency considerations make the hashing approach a robust solution to the problem.
To solidify our understanding, let's walk through a couple of examples. Consider the input array 3, 1, 4, 1, 5, with k equal to 2. First, we construct the frequency map 3, 1, 1, 2, 4, 1, 5, 1. Next, we iterate through the map. For the number 3, we check if 3 plus 2, which is 5, exists in the map. It does, so we increment the counter to 1. For the number 1, we check if 1 plus 2, which is 3, exists. It does, so we increment the counter to 2. For the number 4, we check if 4 plus 2, which is 6, exists. It doesn't. Similarly, for the number 5, 5 plus 2, which is 7, does not exist. Thus, the final count is 2. Now consider another example, the array 1, 2, 3, 4, 5, with k equal to 0. The frequency map is 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Since k equals 0, we need duplicates to form valid pairs. However, no number appears more than once, so the count remains 0. To optimize further, we could avoid rebuilding the frequency map if multiple test cases share the same array. Additionally, we can return early for cases where k is negative or the array length is insufficient, saving unnecessary computation. This solution efficiently solves the problem of finding K-diff pairs in an array using a hash-based approach. The method leverages the collections counter class to count the occurrences of each number in the input array. This allows us to efficiently check for pairs that satisfy the k-difference condition. The function begins by checking if k is negative. Since the absolute difference cannot be negative, it immediately returns 0 in such cases. Next, the counter object number_counts is created to store the frequency of each number in the array. The variable count is initialized to 0 to keep track of the number of valid k-diff pairs. If k equals 0, the problem reduces to finding numbers that appear more than once. This is done by iterating through the keys of number_counts and checking if their frequency is greater than 1. For each such number, count is increment. For k greater than 0, the algorithm iterates through each unique number in number_counts and checks if number plus k exists in the hash map. If it does, it increments the count. This ensures that each pair is counted only once, as the iteration is restricted to unique numbers in the input. The overall time complexity of this solution is O(n), where n is the number of elements in the input array. This is because both the creation of the counter object and the subsequent iterations are linear in time. The space complexity is also O(n), due to the storage requirements of the hash map. By handling both k equals 0 and k greater than 0 cases separately, the solution ensures correctness and avoids unnecessary computations. This approach is both efficient and easy to understand, making it well suited for the problem's constraints. Here, we start by importing the necessary libraries and defining our solution class with the method findPairs. This method takes two inputs, an array of integers nums and an integer k, which represents the difference we are looking for. The first thing we do is check if k is negative, because a negative difference doesn't make sense in this context. If k is less than 0, we immediately return 0. Next, we create a hash map called numberCounts to store the frequency of each number in the array. This is done by iterating through the array and using the getOrDefault method to increment the count for each number. After building this frequency map, we initialize a variable count to 0. This will help us track the number of valid K-diff pairs. Now, we handle the case where k is 0. If k is 0, we need to count how many numbers appear more than once in the array. To do this, we iterate through the keys in number counts, and for each key, we check if its frequency is greater than 1. If it is, we increment our count variable. For the case where k is greater than 0, the logic is slightly different. We iterate through each unique number in the frequency map, and for each number, we check if the map contains the number plus k. If number plus k exists in the map, it means we have found a valid K-diff pair, so we increment the count. Once this loop is complete, we return the total count of valid pairs. This implementation ensures that we handle both cases, when k is 0 and when k is positive, efficiently using the properties of the hashmap to check for existence in constant time. Finally, the method concludes by returning the total count of K-diff pairs found in the input array. To solve this problem, we start with the example where nums is 1, 2, 3, 4, 5, and k is 2. The first step is to check if k is greater than or equal to 0, which it is in this case. Next, we create a frequency map using the counter class to count how many times each number appears in the array. The result is a dictionary where each key is a number from nums, and the value is its count. Since all numbers in this array are unique, the frequency map is 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. We then initialize a variable, count, to 0. This variable will keep track of how many K-diff pairs we find. Now, the plan is to iterate through each unique number in the frequency map and check if adding k to that number results in another number that exists in the map. Starting with number equal to 1, we calculate 1 plus 2, which is 3. Since 3 exists in the frequency map, we increment the count to 1. Next, for number equal to 2, we calculate 2 plus 2, which is 4. Again, for exists in the map, so we increment the count to 2. For number equal to 3, we calculate 3 plus 2, which is 5. Since 5 is in the map, we increment the count to 3. When number is 4, we calculate 4 plus 2, which is 6. Since 6 is not in the map, we do not increment the count. Finally, for number equal to 5, we calculate 5 plus 2, which is 7. Since 7 is also not in the map, we do not increment the count. At this point, we have finished iterating through all the unique numbers, and the count is 3. This means there are 3 K-diff pairs in this example. Now, let's look at a different example where nums is 1, 3, 1, 5, 4, and k is 0. We start by confirming that k is greater than or equal to 0, which it is. Then, we create a frequency map for the array, which results in 1, 2, 3, 1, 5, 1, 4, 1. This shows that the number 1 appears twice, while all other numbers appear only once. We initialize the count variable to 0. Since k is 0, we are looking for numbers in the frequency map that have a count greater than 1, as this would indicate a pair where the difference is 0. Starting with number equal to 1, we see that its frequency is 2, which is greater than 1, so we increment the count to 1. For number equal to 3, its frequency is 1, so we skip it. Similarly, nums 5 and 4 also have frequencies of 1, so we skip them as well. At the end of this process, the count remains 1, meaning there is 1 K-diff pair in this example. In the final example, we have nums equal to 1, 2, 3, 4, 5, and k equal to -1. The first step is to check if k is greater than or equal to 0. Since k is -1, this condition is not satisfied. In this case, we immediately return 0 because a negative k does not make sense in the context of this problem. The result is a count of 0, as no K-diff pairs can exist when k is negative. To analyze the time complexity of our solution, let's break it down step by step. First, we use the counter function to count the frequency of each number in the input array nums. The counter function iterates through the array once, so this step takes n time, where n is the length of nums. Next, we iterate through the unique elements stored in number_counts, which is the dictionary created by counter. In the worst case, all elements in nums are unique, so the size of number_counts is also n.
If k is 0, we check if any numbers appear more than once, requiring O(n) operations. For k greater than 0, we check if number plus k exists as a key in the dictionary. Since dictionary lookups are O(1), this step still takes O(n) for the iteration. Combining these, the dominant operation is the iteration through number underscore counts, which takes O(n). Thus, the overall time complexity of the solution is O(n). Now, let's focus on the space complexity. The main contributor to space usage is the counter object, which stores the frequency of each unique number in the input array. In the worst case, all elements in nums are unique, so the counter object requires O(n) space. Other variables, such as count and the loop variables, use a constant amount of space, which is O(1). Since the space complexity is dominated by the counter object, the overall space complexity of the solution is O(n). This efficient use of space makes our approach scalable even for large input arrays.
Let's compare our optimized approach to a brute force solution.
A naive method would involve iterating through all possible pairs of elements in nums, checking if their absolute difference is equal to k, and ensuring that each pair is counted only once. This requires two nested loops, where the outer loop runs O(n) times and the inner loop also runs O(n) times. Checking for duplicates takes constant time per pair, but the overall time complexity for this approach is O(n squared, which is quite inefficient for large arrays.
In contrast, our optimized approach uses a counter object to store frequencies of elements and checks for valid pairs in a single iteration through the keys.
This eliminates the need for nested loops, reducing the time complexity to O(n).
The space complexity is also O(n) due to the counter object. Clearly, the optimized solution is far more efficient in both time and space.
Finally, let's analyze the best, average, and worst-case scenarios for our algorithm. In the best case, if the input array nums contains only one element or if the value of k is less than 0, the algorithm terminates early, resulting in a time complexity of O(1). For the average and worst cases, the situation occurs when all elements in nums are unique. Here, constructing the counter object requires O(n) time, and iterating through the keys of number underscore counts also takes O(n) time. The space complexity in these scenarios remains O(n) due to the storage of unique elements in the counter. To mathematically validate the big O, we note that the counter processes each element in O(n) time, while the iteration over keys involves constant time lookups, contributing another O(n). Adding these gives a total time complexity of O(n plus n), which simplifies to O(n). The space complexity is proportional to the size of number underscore counts, which is O(n). This linear time and space efficiency highlights the strength of our approach compared to the brute force method. When solving the K-diff pairs in an array problem, there are a few common mistakes that are important to avoid. First, many people confuse unique pairs with duplicate values. For example, in an array like 1, 1, 1, with k equals 0, there's only one valid pair, 1, 1. Counting this pair multiple times violates the requirement to only count unique pairs.
A good fix is to use a frequency map to track occurrences of each element and ensure that each pair is counted only once. Another common issue is not handling edge cases for k. Some might assume that k is always positive, but the problem explicitly states that k must be greater than or equal to 0. If k is negative, it's invalid, and the correct approach is to return 0 immediately since a negative difference doesn't make sense in this context. Finally, inefficient solutions using nested loops can lead to time complexity issues. Using O(n squared complexity for large arrays, such as when the size approaches 10 to the power of 4, will be too slow. Instead, leveraging a hash map or a two-pointer technique can reduce the time complexity to O(n) or O(n log n, making the solution much more scalable. Another area where mistakes often occur is in the two-pointer approach.
If both pointers are advanced simultaneously without ensuring the difference equals k, this can lead to missed pairs or incorrect results. Instead, the pointers should be adjusted based on whether the current difference is less than, equal to, or greater than k. This way, you ensure that all valid pairs are considered. Overcomplicating the hash map solution is another common pitfall. Some developers try to store all pair combinations in the hash map, which not only increases memory usage unnecessarily but also complicates the implementation. The better approach is to use a simple frequency map, focusing only on element counts and checking for number plus k, or handling k equals 0 scenarios appropriately.
Streamlining the hash map solution in this way improves efficiency and keeps the implementation clean.
For interviews, this problem provides a great opportunity to demonstrate several key skills.
One of the most important is pattern recognition.
This problem is a classic example of using hash maps for counting and efficient lookups, which is a common strategy in array-related problems.
Recognizing when to use a hash map instead of brute force shows your understanding of algorithmic optimization. Another important aspect is edge case awareness.
Being prepared to discuss scenarios like empty arrays, duplicate values, or invalid k-values can impress interviewers by showing your thoroughness and attention to detail. Additionally, you should be ready to discuss time and space trade-offs. For example, you might explain why hash maps are more efficient than nested loops for this problem, or how sorting impacts space complexity. Finally, it's helpful to generalize this problem to related scenarios, such as finding pairs or groups that meet specific conditions, like in two-sum variants. This shows your ability to apply the same principles to different challenges. The concepts in this problem closely relate to several other problems on LeetCode. For example, LeetCode 1, two-sum, also relies on hash maps to efficiently find pairs, though the goal there is to find a specific sum rather than a difference. LeetCode 15, three-sum, takes this further by requiring you to find triplets that meet a condition, adding another layer of complexity. Similarly, LeetCode 18, four-sum, extends the challenge to finding quadruplets, emphasizing the need for efficient combination generation. Lastly, LeetCode 454, four-sum 2, builds on these ideas by using hash maps to efficiently find tuples across multiple arrays. These related problems highlight the importance of mastering pair finding techniques and understanding how to adapt them to more complex scenarios. There are multiple approaches to solving the K-diff pairs problem, each with its own trade-offs.
One option is to use sorting in two pointers.
Sorting the array simplifies duplicate handling and allows you to use two pointers to find pairs with a difference of k. This approach has a time complexity of O(n) log n, due to sorting, and a space complexity of O(1) for in-place sorting. However, the pre-processing step of sorting adds extra time.
Another approach is to use a hash map for frequency counting. This involves storing the frequencies of elements and checking for number plus k.
This method achieves O(n) time complexity and O(n) space complexity, making it very efficient for larger inputs. The trade-off here is the additional space required for the hash map. Finally, while brute force is an option, it's not recommended. Using nested loops to compare all pairs results in a time complexity of O(n) squared, and a space complexity of O(1). While simple to implement, it's highly inefficient for large inputs and should be avoided in favor of more optimized methods.
Great job!
To summarize, we tackled the K-diff pairs in an array problem using a hash map for efficient frequency counting. This solution demonstrated the importance of understanding edge cases and optimizing for both time and space.
Thanks for joining, and don't forget to like and subscribe for more coding tutorials. Keep coding, and see you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!